series. My name is Kim Hissong, and I'm the Associate Vice President for University Advancement here at St. Lawrence. And we're very excited to be offering this lecture series as a way for alumni, parents, and friends across the country to experience today's St. Lawrence classroom firsthand. Before we get started, I'd like to cover just a few technical items that should help make your webinar experience a more enjoyable one. At various points throughout tonight's lecture, we will pause and invite you to make comments and to ask questions. And at that time, you can do that in one of two ways. You can either raise your hand using the hand icon that you should see in the bar at the top of the navigation pane. The icon is a small hand. It should be in blue or orange towards the bottom of that bar. You can click it once to raise your hand, and when you're called on, you'll be unmuted and can ask your question directly. If you prefer, you can also type in a question or comment, and we will get to those as well throughout the lecture. A few tips about the audio. If you happen to be using the audio through your computer, just know that you have to have a built-in microphone or an external microphone in order to ask us questions. Otherwise, you'll be able to hear us, but unfortunately we won't be able to hear you. If you are using your telephone audio, if you happen to have your phone on speaker during the webinar, again, in order for us to hear your question, you'll likely need to take the speaker off during that time so that we can hear you. We recommend that during the lecture you minimize the navigation pane that's up in the upper right-hand corner. You can use the orange arrow at any time to minimize the pane, and if you need to maximize the pane at any point to ask a question, to raise your hand or to type in a question, simply use the orange arrow to maximize it. So without further delay, I'm pleased to introduce our lecturer for the evening, Dr. Jeff Chiarenzelli, the James Henry Chapin Professor of Geology and Mineralogy. Jeff attended St. Lawrence. He's an alumnus, graduated in the class of 1981, and pursued his graduate studies at Carleton University in Ottawa and the University of Kansas. Here at St. Lawrence, Jeff teaches courses in mineralogy and geochemistry and supervises a wide variety of undergraduate research, including an active research program focused on Adirondack geological and environmental issues. Tonight's lecture is entitled New Insight into the Geologic History of the Adirondacks. So welcome, Jeff.
Thank you very much. Thank you, Kim. Thank you for being here and setting this all up. Thank you, everyone who's listening out there, for attending this lecture. I'll try and make it educational and fun as we go through this. And Kim's absolutely right. I am fascinated with the Adirondack region. I always have been, and I have the good fortune to study geology and environmental science in the region. And I just want to bring to your attention a few things. So I'll just make a quick roadmap for you. I'm going to talk a little bit about how I became interested in the Adirondacks, and that has some ties to my time spent here as a student. I'd also like to do a little bit of myth busting. There's some commonly held beliefs about the Adirondacks that need to be touched up a little bit. I'd like to put the region in its geologic context, what was happening at the same time around the world. Then I want to talk about a tool that's really kind of near and dear to me, zircon geochronology. Zircon is a trace mineral that occurs in many different rock types. And then I want to talk about some of the implications of the rocks for more practical things, farming and mining, and then eventually get into some of the new information on some of the minerals and ores. And like Kim said, we'll try and stop at various times throughout the lecture to give you a chance to ask any questions or raise any comments. So I think I have always had an interest in natural history, and a lot of it was actually due to Jack London. I had an anthology when I was a small boy, and I read these stories like To Build a Fire and Lost Face, which just had me absolutely fascinated about northern regions. And I loved that book, and I read it over and over again. And it even led to one winter when I decided, and my parents can attest to this, I think my mom has photographic proof, where I decided to sleep outside all year round. And I think she has a picture of me with snow on top of the sleeping bag in my head. Next slide. So after spending some time at St. Lawrence University, I had the great fortune to apply for graduate school, and I was accepted at many schools in various localities. But I got a call one day from a man named Al Donaldson, who was to become my master's supervisor up in Ottawa, Canada at Carleton University. And he told me that if I came to Carleton University, that he would send me up to the Arctic that summer. And a few weeks after graduation in mid-May, I showed up at his house in Ottawa and with a pack of equipment, and he just kind of laughed and said, well, things haven't really defrosted yet. The lakes are all frozen, the ground is covered with snow. Why don't you come back in a month? And I did, and then I was able to travel to the Arctic. And one of the first things I learned about the Arctic, at least the Canadian Arctic, is that it's probably more water than land, as you can see in that photograph outside of the float plane. Just an amazing amount of fresh water. And one of the other things that I learned is that aerial photographs taken in August don't necessarily reflect the level of the water in June. So we did an awful lot of wading through some ice water, which built character. Next slide. And then I also learned that there are biting insects that love to feast on humans, and black flies and mosquitoes became my enemies. And so little did I know, but for about 25 years of my life, I participated in a mapping program of the Adirondacks Greenstone Belt in the Hurwitz group, which is a paleoproterozoic sedimentary group, and we started up near Rankin Inlet on the coast of Hudson's Bay, and then we worked our way through those yellow inliers all the way down to the Saskatchewan border. And it was a major event for me in terms of learning about geology and learning how to operate in very remote areas. And always treasured the opportunity to do that, and I'll be going back next summer and taking some students with me. But one of the things that kind of set me on the path to becoming very infatuated with the rocks in the Adirondacks was participating in what was known as the Crystalline Rock Project. In 1984, the New York State Geological Survey, along with most geological surveys in the country, was given money to investigate high-level radioactive nuclear waste repository sites. The New York State Survey, knowing darn well that the federal government would never cite a nuclear waste repository in a park, in a very wet park, had us map, about 12 of us graduate students, map an area in the Adirondacks between Old Forge and Blue Mountain Lake. And my boss at the time was Karen Olson, who was 1 year ahead of me in school. She graduated in 1980 from St. Lawrence. And they put us up in an old inn, the Deerhead Inn, in Big Moose Station, and that's a photograph of it there. And I am absolutely astounded that the porch did not fall off, because we loaded it up with so much rock. You can see it there on the right-hand side. And they bought us a cook. They hired a cook for us, and that's a picture of our cook, a young man named Jonathan Halpert, who lied thoroughly on his resume and said that he had cooked for large groups of people. And we knew it was going to be a problem the very first morning when we were served refried spaghetti for breakfast. And while we worked for the Crystalline Rock Project, we spent every day out in the woods in that area. Sometimes we'd set up fly camps and stay there for 3 or 4 days in very remote areas in the western Adirondacks and look at the rocks. And one of the things that bothered me about my time there is that the rocks were highly deformed, and it was very difficult to tell the original relationships, what intruded what was deposited on what. So that brings us to this tool that I wanted to talk a little bit about, and this is zircon. That's a little pile, that little pile of lavender sand, are zircon separated from about 50 pounds of granite. Zircon is a trace mineral. It contains trace amounts of uranium and thorium, which over time decay to lead, and so it allows us to use the uranium, thorium, lead system to date rocks. And this is particularly important in the Precambrian for reasons I'll talk about in a minute. So the geologic timescale has been built up over many, many years, and basically the closer you get to the present, the more we know. And the Paleozoic era, which is shown in the center column there where it says Cambrian, Ordovician, Devonian, that was all subdivided on the basis of changes in the faunal record. So you'd find one different type of fauna in the Cambrian than in the Ordovician. So it's fairly well known and fairly well subdivided. However, the Precambrian, which makes up about 95% of geologic time, was not all that well known because there are, aside from single-celled organisms, not much in the way of a fossil record. So although we're able to subdivide, using fossils more recent geologic time to a high degree, it wasn't true for the Precambrian. So it was this great big question mark. And then all of a sudden, this technique to use zircons as a way to date was invented and kind of revolutionized what we know about the early parts of Earth's history. So there's a picture of a zircon. It's one that I dated many years ago, and it's been embedded in epoxy and then sectioned halfway through. And you can see the shape of it. It's a long prism with dipyramidal terminations on either end. And because it's embedded in epoxy, we can see the internal features, and you might be able to see the kind of pointed zones of how it grew. And you can see the fractures that cut across it. In the center there, you can see inclusions, other minerals that were included while the zircon was growing. Well, the technology for dating zircons has advanced to the point where we can take a relatively small spot and focus it on the grain with a laser and ablate the material. So in the center, there's a core which gives an age of 1142 million years. However, the rim is 1049 million years. So there's almost 100 million years between the core and the rim. So this one individual crystal tells us an awful lot about the source of the rock and also the time of metamorphism. So these crystals, using this technique to focus on very specific areas, can tell us an awful lot about the history of an area, and that happens to be a zircon from the Adirondacks. And so because of my interest in the Adirondacks and the frustration I felt having a hard time figuring out what the primary relationships were, I decided to go to graduate school at the University of Kansas, where they had a very good geochronology lab. And although my project was actually based in northern Saskatchewan, I managed to bring in a number of samples from the Adirondacks, and we started the first uranium-lead zircon dating program in the Adirondack region. And we were able to date over 50 rocks, and I initially worked with Phil Whitney and Ingvar Saxon from the New York State Geological Survey, and then Jim McCollum from Colgate University. All these folks are now retired. Ingvar happens to be deceased. And so it was the first systematic evaluation of the entire Adirondack Massif and kind of set the stage for the studies that would come after. So now what I'd like to do is a little bit of myth busting. You may have heard certain things about the Adirondacks, and some of them are patently untrue. Others need a little bit of tweaking. So let's see. Number one, the Adirondacks are made up of some of the oldest rocks on Earth. Well, that's not really true, and we'll get into that in a minute. The Adirondacks are made up of the same rock as the moon. That also needs to be tweaked a little bit. There's a ring of truth in it, but I'll elaborate. The third is that the Adirondacks are part of the Appalachian mountain chain. That is patently false, although it does occur on some signs in the park. Number four, The geology of the Adirondacks is too complex to be understood, and I think we can make some statements about how that is a misconception that was propagated before we had the tools to accurately understand it. And then number 5, the geology of the Adirondacks does not have a modern analog, and I'd like to propose a modern analog to explain what we see here. So number 1, oldest rocks on Earth. Not so much. It's really an old idea based on the extent of deformation and metamorphism. Before we had uranium, lead, zircon dating in the Precambrian, we had no way to subdivide the Precambrian, so a simple assumption was made, and it was the rocks that have suffered or enjoyed the most deformation and metamorphism would be the oldest. However, it turns out, although the rocks here are old, between 1.0 and 1.4 billion years old, they are nowhere near the oldest rocks on Earth. The oldest intact rocks that we've been able to find up in New Quebec are about 4.2 billion years old. So the rocks in the Adirondacks are only about 1/4 to 1/3 as old as some of these older rocks. So there's the geologic time scale, and that shows the approximate age of the rocks in the Adirondacks. They're about 1 billion years old on the left-hand side. And that shows the rocks in New Quebec at Porpoise Cove that have been recently dated at about 4.2 billion years. So there's a lot of history between the formation of the Earth, the formation of the first crust, and the Adirondacks. So they are nowhere near the oldest rocks on Earth, but they are old. And this is a pamphlet that was actually produced in our own department back in the 60s by Robert O. Bloomer and William T. Elverty. And the title of it, as you can read, is The Adirondack Region, 3 Billion Years in the Making. And again, this misconception was only based on the fact that we didn't have a tool to understand and date the Adirondacks. And because of their extensive deformation and high-grade metamorphism, they were considered to be some of the oldest rocks. So, moon rocks. Well, some of the rocks on the moon are close to the Adirondack rocks, but not exactly. The high peaks, Mount Marcy area and all the other high peaks, are underlain by a rock type called massif anorthosite. You can see it up there in the upper right. It consists of extremely large crystals of plagioclase feldspar, about 90% plagioclase, and a few other mafic minerals like pyroxene or sometimes hornblende or olivine. The lunar highlands, those light areas down on the lower right, are underlain by anorthosite as well. However, the Adirondack anorthosite is much younger, only about 1/4 of the age, and it is chemically distinct. The Adirondack anorthosite, the plagioclase in that rock, is a sodium-calcium plagioclase, whereas those on the moon are very extreme. They're very calcic with very little sodium. And, of course, the difference in age. However, there is a very interesting problem that remains and we don't completely understand, and it turns out that most of the world's exposed anorthosite occurs in the Grenville province. The Grenville province there is shown in the light shading, and all those yellow bodies are anorthosite, and you can see they extend up into what's called the Nain province and then down through the Grenville province all the way into the Adirondack region. You can see the large Marcy anorthosite massif. The second largest one is the Oregon Dome, which is down near Snowy Mountain Lake. So we still don't understand why this vast amount of anorthosite formed in the Grenville province and why it's restricted spatially and temporally to that area. Part of the Appalachians. Well, there is actually very little deformation in the Precambrian rocks of the Adirondack region during the Appalachian orogenic events. It actually served as a rigid buttress around which the rocks were kind of warped during the Appalachian events. And even further, the Appalachian events occurred long before the uplift of the present Adirondack Mountains. One thing you should be aware of is that the actual physical topographic expression of the Adirondacks did not develop until about 180 million years ago. In other words, those rocks were planed off and eroded flat almost to sea level for a long, long time. And then about 180 million years ago, for reasons that are just beginning to become understood, it started to dome upwards. So the Adirondacks are really old rocks, and the mountains are really new. So there's a satellite photo that shows the Northeast up in Tickleback down towards Virginia, and that is the, one more, thank you, that is the extent of Appalachian deformation. So you can see right there that just to the left of the Appalachian deformation, you can see the ridges. Well, those are corrugations in the sedimentary cover that was deposited on North America. And because of the mountain building event, those rocks have been tilted and folded and corrugated into those very tight patterns. And anyone who's ever driven through Pennsylvania knows that as you go through Pennsylvania, you go through many tunnels, and many of those tunnels go right through those structures. But on the upper left, the Adirondack region, most of the Finger Lakes, western New York, are undeformed. They were essentially undeformed during the Appalachian event. So that yellow line kind of marks the edge of the Appalachian deformation front. Too complex. The rocks in the Adirondacks are highly deformed. Some of them are very highly metamorphosed. Some have even melted. And to a large extent, the original relationships, such as intrusive relationships or sedimentary relationships, what's deposited on what, have been obliterated. All the contacts have been translated to the point where they are straight, and you can't tell who intruded who. However, there are places where there are some very, very good exposures of original relationships. So there's a rock type, and this comes from Pyrite, New York, from the pyrite mines. And you can see a very, very tight isoclinal fold developed in those mustard-colored gneisses, and you can see the hammer. But if you blow up on that particular isoclinal fold, you can see compositional layering. So just above the end of the hammer is a more resistant unit that's composed of quartzite, and below it is a politic gneiss that's now garnet and silmonite. So we know that we had these mud-sand couplets deposited over and over again. So even though the rocks have been highly metamorphosed and now are composed mostly of high-grade metamorphic minerals, we can still see, even though they're folded, what the original relationships were in some circumstances. Some of the rocks, like you may have heard of the Poplar Hill gneiss if you're a geology person. The Poplar Hill gneiss, because of its composition, underwent partial melting. Those white layers in the darker matrix are areas of anatectic melting. The rock started to partially melt, and that material was sweated out of it during deformation and metamorphism. And one of the most interesting features that has been recognized, and this was first recognized by Ingvar Isaacson many years ago, right outside of the Zinc Corporation of America's gates is a carbonate unit, a marble unit, in which people have interpreted these sedimentary structures as stromatolites. And so that particular domed downward feature with the fine lamination is interpreted as a stromatolitic horizon. Since they've been identified by Ingvar, they've been found in the subsurface as well. One of the fascinating things is that they are not in their growth position. In that particular place, they are turned upside down. They're on the overturned limb of a large fold. And as my good friend Bill D. Lorraine, who works at the zinc mine, says to me all the time, there's only one place in the Adirondacks where we know which way is up, and in that place, up is down. Next slide, please. And, but there are places in the heart of the Adirondacks where you can see the original relationships, and they're absolutely pristine. This is from the Benny's Brook slide, which is very close to Keene Valley. Lately, I've been working the slides with some of my students, and the exposures are just amazing. And after Hurricane Irene, there's something like 45 news slides that were created. And essentially they are just absolute sidewalks that you can walk up, and the rock is totally exposed. And so what I have there labeled as number 1 is massif anorthosite. Number 2 is the gabbro, which intruded it. Number 3 is a basaltic dike, which intruded both those rocks. Number 4 is another basaltic dike that intruded all of the 3 previous intrusions and split dike number 3. So you can actually see the primary relationships. You don't even know those rocks are metamorphosed, and yes, unless you look at them very closely, and you can see some metamorphic garnet in some areas. So you can see some features in places. So is there a modern analog? Well, I would argue there is, and I've been one of the people who've been trying to pin it down and provide some constraints on it. And one of the simple things that gives us a clue into what the modern analog might be is the sedimentary rocks, the rocks that have been metamorphosed at high grade, but because of their extreme composition, they can be interpreted in no other way. For instance, quartzite, which is a very hard, resistant metamorphic rock composed of 90% or more quartz, had to at one time have been a sandstone. So if you see quartzite, you know that you were dealing with sand-sized fragments of quartz in some type of environment where they could accumulate. Same is true for marble. Marble is one of these rocks because of its calcite and dolomite-rich composition, can be nothing else but limestone. And we know of environments, the shallow marine environments that limestone forms in today. And even probably more constraining are the evaporite minerals that occur in the mine at Belmont. There's some units that are almost entirely made out of evaporite minerals. Gypsum converts to anhydrite as it becomes dehydrated, and there's thick anhydrite deposits. So not only can we say there was a shallow sea in the area a long time ago, but we know that it had to dry up to crystallize all these evaporitic minerals. So by using these sedimentary rocks, we can get a very good idea of the environments that existed before the mountain building event, exactly what happened before there were mountains here. So we can propose tectonic models, and no one's saying that they're 100% correct, but these initial tectonic models will be tested and refined and changed if they are wrong. And there's one of my former students. She's now at Temple University studying geothermal geology. Her name is Rosalind Busso. She's 1.676 meters, and she's standing in front of one of the marble outcrops along Route 11 near DeKalb. Rosalind is from Kenya and was along for me on a Thanksgiving trip down to central New York for a Thanksgiving dinner, and we stopped and took that photograph. And one of the cool things about that photograph is you can see the layering and the folding in the bottom unit, but there's also an overlying marble unit. And so that's a contact between two different types of limestone, both of them highly deformed. Any questions thus far?
Okay, so just as a reminder, if you do have questions or comments, you can either raise your hand using the hand icon, or you can also type your question in. So we'll just see if anyone has raised their hand. Go look down through here. Okay, it looks like Peter Larrabee has a comment or question. Peter, go ahead. Has a comment or question. Peter, go ahead.
Actually, I hit the button incorrectly. I apologize.
Peter, did you have a question? Okay. Well,
I think he may have hit it.
I think Peter might have hit that by accident, so we'll just we'll keep going and see if we've got anyone else here. Okay. Okay, so we have a question from Doug Reed. It says, how old is the moon distinctly different on northosite?
Hi, Doug. Thank you for attending, and thanks again for hosting us at Caspian Lake. That was wonderful. The anorthosite on the moon has been dated at about 4.4 billion years. The anorthosite in the Adirondacks is about 1.1 billion years old, so the anorthosite in the lunar highlands is about 4 times as old as what we see in the Adirondacks.
Then we have another question here. This is from, it looks like Dwayne Epstein. It says, how do you separate, you might have to pronounce this,
zircon
crystals,
yeah.
50 pounds of granite?
Okay, I'm sure that's probably Dwayne Epler, and I will tell him that you have to strike it very hard, and not with your fist or your foot. You have to use a sledgehammer first to break it into reasonable sized chunks. And then when you get it down to about golf ball size, there's some equipment that we use. And one of the pieces of equipment is a jaw crusher. And that'll take it down to about fingernail sized. And then there's other pieces of equipment that'll disaggregate it further. And one of the things that's always been fascinating to me is that they come out perfectly preserved. All their crystal faces are preserved, and they usually don't smash up and fracture. And the reason for that is zircon is one tough mineral. It has a hardness greater than quartz. It doesn't have any pronounced cleavage or fracture direction, so it's very durable. Once you powder the entire volume of rock, you have to use what's called a Wolfley table, some way to separate out the more abundant lighter minerals like quartz and feldspar. Once you do that, you're left with the heavier minerals, and you use magnetic separation in heavy liquids to separate out the zircons. And the reasons we can do that is because the zircons have such a high specific gravity. They have a specific gravity on the order of about 4.3 grams per cubic centimeter, which is higher than most mafic minerals and certainly higher than most felsic minerals. So it's a long process, and when I actually did this at the University of Kansas, it was a 24-hour job per sample.
We have another question comment from Robert Boise. It says, Quebec and the Adirondacks seem pretty close to have rock aging 1.4 billion and 4.2 billion years in difference.
Good question, Robert. How are you? It turns out that New Quebec, where they found the 4.2 billion year old rocks, is actually across a fundamental boundary. There's a boundary called the Grenville Front Tectonic Zone, and on the other side of that is what's known as the Superior Province. And the Superior Province, or craton, is one of the earliest cratons that formed in Earth's history. So in New Quebec, which is way up near the Belcher Islands on Hudson's Bay, there are some zircons that are of that age and very, very old, but the distance is much greater than you might think, and there's a fundamental tectonic boundary between the two provinces.
Graham Baird asks, where on the Earth today can we find environments that have sandstone, marble, and limestone like what we find in the Adirondacks?
Well, there's actually many places where you can find that particular sequence. It's pretty common on the margins of continents. You can find it in places like the Red Sea, where you have active rifting right off the coast of North America. So there's many different tectonic environments where you can find all three of those rocks together.
Just a comment from Doug Reed that says, thank you, Jeff. Love those much older moon rocks. Oh, okay. Here's a question that says, hi, Jeff. I'm really enjoying your lecture, and I'm wondering if you can help jog my memory about a field trip that Dr. Romy led when I was at St. Lawrence. We were somewhere northwest of Albany, and I think we visited an outcropping of pillow basalt. And I was wondering, is my memory accurate? And two, do you know more precisely where that is? And is it considered part of the eastern edge of the Adirondacks?
Oh, great question. Yes, I can help out. I've been there myself. It's a very small outcrop called Stark's Knob in a place called Schuylerville, and it's just a little bit east, maybe 10 miles east of Saratoga. And it's actually been worked on by folks at the New York State Museum. Ed Landing worked there, and he was actually able to recover gastropods from the sediment infill around the pillows. And their thoughts are that those pillow basalts were formed on the bottom of a large basin that was formed in front of the encroaching tectonic arc, which was then thrust up on North America. So cracking of the crust led to fractures, which allowed basaltic magma to make its way to the surface. It formed on the bottom of the ocean and then was included in the thrust sheets that were thrust over the edge of North America.
And that was a question from Charlie Roth. So the next question is Chris Dahl as a follow-up, since my question was already asked. This next question is, what is a craton, Superior versus Granville?
Right, yes. It's something that I haven't explained yet. It turns out that back in the 60s, at the Canadian Geological Survey, there was a man named C.H. Stockwell, and he did a simple exercise. He went out and he collected samples from all over the Canadian Shield, and he analyzed them by a technique called potassium argon and got cooling ages. They don't really record the age of the rocks, but when the last time the rocks were elevated to high temperatures. And using those cooling ages, he divided the Canadian Shield into a number of structural provinces. So the Grenville province was last formed about 1 billion years ago. The Superior province on the other side of the Grenville tectonic zone was deformed during the Archean. So with these different dates of deformation and metamorphism from Stockwell's data, we have subdivided the Canadian Shield into a number of cratons. And what they really are, though, is kind of the nucleus of North America, the oldest rocks in the center of the continent.
It looks like we might have one more question. This one is from Peterson Mena, asking, are zircons found in all the 3 major types of rocks, and how did they develop to infuse rocks?
I should ask Peterson that question because I'm pretty sure he knows it. Yes, indeed, they are found in all 3 major types of rocks, igneous, metamorphic, and sedimentary. And however, there are some caveats. Because zircon is a silicate mineral, in igneous rocks it mostly occurs in igneous rocks that have a lot of silicon, so the felsic rocks and the intermediate rocks. They're less common in the mafic and ultramafic rocks. They're common in sedimentary rocks, and we're going to talk about that as when I get into detrital zircons down the road, and they are also found in metamorphic rocks.
All right, we'll head back to the presentation and then we'll take some more questions in a little bit.
Great, well let me try and put what we see in the Adirondacks in kind of a continental perspective and then maybe a global perspective. So there's the Adirondack Massif. And if you can see it well enough, you can see that it's colored. And rocks of the Canadian Shield, they're shown in different colors related to their age. And you should know that you can trace these underneath the younger cover rocks shown in white. So if you go to Kansas and you drill a hole deep enough, you will hit Precambrian rocks. So the Adirondacks are part of the exposed Canadian Shield, and they are connected through the Frontenac axis in the Thousand Islands. If any of you has a camp there who have spent any time on the St. Lawrence River, you'll notice that the river there splits into a number of different channels, and there's virtually 1,000 islands composed of pink granite, and those are the rocks that connect the Adirondack Massif to the greater Grenville province. So they are part of the Canadian Shield. They're connected through the Frontenac axis. So here's a little blow-up from Jim McClellan, a paper that Jim wrote in 2010. And it shows the Grenville province in gray. So you can see the Adirondack region labeled AD and the greater Grenville province. And then that feature called the Grenville Front that I was telling you separates the Superior province from rocks that are much younger in the Grenville province. But one thing that I wanted to point out is the number of black, they're labeled as Appalachian Mesoproterozoic inliers. those are parts of the Grenville province that were caught up in the Appalachian event. So those rocks are Grenville basement rocks, just like those in the Adirondacks that have been folded and thrusted and metamorphosed during the Appalachians. And if you look up towards New York, you'll see that some of those rocks east of the Hudson River and west of the Hudson River down near New York City are inliers. So if you go to New York City and just go north 20 or 30 miles to the Hudson Highlands, you can see Grenville rocks that have been deformed during the Appalachian event. They were on the edge of the continent, so they were vulnerable to additional deformation and metamorphism. So there's the outline of New York. So the Grenville province, the Adirondacks are part of the Grenville province, but so are all those inliers in the Appalachian Mountain Belt. And the other point that I want to just kind of try and bring home is not only do those Grenville rocks occur in the Adirondacks, they occur throughout New York State, but they're buried underneath younger flat-lying Paleozoic rocks. So if you went to Syracuse, New York, and you were able to drill through the Silurian, Ordovician, and Cambrian rocks, eventually you would hit the Precambrian basement. The reason we see them in the Adirondacks is, again, because the area has domed up. It's a large domal structure. The younger rocks have been stripped off, and now we can see into the basement rocks. However, perhaps even more interesting is the fact that the Adirondack region was in the center of a massive continental collision. In fact, it's part of this worldwide chain of mountain belts that form more or less at the same time. You can probably see the star there, right there. And you can see that the basic convergence was in that area. So you had Laurentian, or North America, moving up against Amazonia, and these continents were colliding, and the Adirondack region was caught in the middle. So it's part of a worldwide belt. It is formed because of a continental collision. It was caught in the middle of that continental collision, and when it was all said and done, these Grenville-aged mountain belts led to a supercontinent, and that supercontinent is known as Rodinia. Now, supercontinents have occurred on the Earth's surface from time to time. You're probably familiar with Pangaea. Pangaea was one of the, well, was the most recent supercontinent, but every 400 or 500 million years, for some reason, not fully explained, the continents actually come together and form a supercontinent. We know that some even existed even before Rodinia. And as everything has a life cycle, eventually Rodinia broke apart into its component pieces, and part of that occurred along the Lake Champlain region where we see the Potsdam sandstone. So the Potsdam sandstone was actually put down along the edge of North America that rifted apart when this all broke up. So what does this all mean? Well, it means that the Adirondacks are a very small part of the core of a world-class ancient mountain belt that at one time was larger than the Himalayas. They were worn down to sea level before the Potsdam sandstone was laid on top of them. The Potsdam sandstone was put down in the Cambrian. They form part of the basement upon which the younger sedimentary rocks in New York rest unconformably. They've been exposed by a relatively recent domal uplift as the younger rocks were stripped away. So where we see the basement rocks in the Adirondack region, the overlying sedimentary rocks have been stripped away by erosion. And finally, these rocks are highly deformed and highly metamorphosed because they are virtually the roots of an ancient mountain belt that was an area where these continents collided to form the supercontinent Rodinia. The Adirondacks are of great interest to geologists because they provide a number of things that you really can't access all that well elsewhere. They provide just a fascinating glimpse into the processes in the deep crust. What was the metamorphism like? What was the deformation like? What type of igneous rocks were formed? What happens to rocks that one time were at the crust and now have been put down to the bottom of a plate, of a tectonic plate thrust down? They contain world-class mineral and ore deposits. It's a place where the anorthosite massif and the associated rocks are very accessible. We can go and see them and sample them. And it's also an area of recent domal uplift that is currently not well understood. However, we know that the doming is still going on today because the area is seismically active. Every 10, 15 years we have a relatively large earthquake, and every year there's many, many small earthquakes. So we know that the doming is ongoing and that the area is alive tectonically. Back in 1991, we offered a field conference on the geology and geochronology of the Adirondacks, and it was held at the Colgate camp next to Camp Canaris on Saranac Lake, and we had over 55 participants. People from Russia, from India, from Africa, from Europe, came to Camp Canaris, and we took them on a 7-day trip throughout the Adirondacks. It was so successful that we did it again in 1992, kind of expanded the look at the Adirondacks, and again we had over 50 people come and join us, hosted again at the camp, the Saranac camp of Colgate University. And this continues today. Back in 2008, Dave Valentino and I ran the Friends of the Grenville trip in the Adirondacks. So there's an awful lot of interest among geologists in seeing these rocks, and we're happy to show them off.
We can take a look and see if we have some more questions from the audience. I think we might. Okay, so we have one here. This one's from, it looks like from Peter. He says, are the Belcher Islands impact related?
Well, I'm not an expert on the Belcher Islands, but having said that, it may be that their exposure is impact related. There's a large circular structure on the east coast of Hudson's Bay, and it may be part and parcel of a large impact that caused the Belchers to be exposed. They are highly folded. It's a very interesting area. The islands, if you ever get a chance to look on them and Google Earth, take a look because it's just absolutely fascinating. You can trace the folds right around.
A question from Doug Reed. It says, are there Grenville rocks in the tectonic mountains of eastern, and it got cut off?
Yeah. Yes, there are. In fact, there's a number of inliers up there, and one of the most famous is Stissing Mountain, which is in Pine Plains, New York. But there's also Grenville rocks in the Berkshires, and they extend up into the Green Mountains. So there are an awful lot of Grenville rocks that are exposed in eastern New York, adjacent parts of Massachusetts, Connecticut, and Vermont.
Rajiv Shah asks about the magnitude of the earthquakes that you mentioned in the Adirondacks.
Yeah, one of the largest earthquakes in recent memory was actually up in the Cornwall and Messina area. I think it was 1944. And that particular earthquake had a magnitude of about 5. It didn't cause that much damage. No one died, but there was about, I think, about $5 million of structural damage. Gravestones were rotated. And, you know, interestingly enough, the fault passes within a few kilometers of the Robert Moses Saunders Power Dam. So it is of some concern.
Question from Dwayne Epler. It says 180 million years ago was when Africa was breaking away and setting sail for the east. In this period of tension, as evidenced by the graben in which the Connecticut River flows, what are the ideas regarding the Adirondacks to dome?
Well, the most recent papers have been done by a professor from Syracuse University and his graduate student, was a student here at St. Lawrence University before I started to teach here, And one of the things that they believe is that the Adirondacks are doming related to a hot spot that passed underneath the area, and that hot spot, the meteor, Great Meteor hot spot, is related perhaps to some of the intrusions up in the Quebec area, the alkaline intrusions, maybe even the White Mountain series. So they believe that the doming in the Adirondacks is related to a hot spot that was underneath Laurentia, and the plate passed over it, and the whole area is starting to dome.
Here's a question from Harry Coolin, who says he's a non-geologist, so he's just putting that out there. He says, how was Upper Saranac Lake formed?
To be truthful, I don't know, but I'll take a guess. The Saranac area has very little in the way of bedrock exposed. In fact, it's one of the few places where there's some active agriculture, tree farms, potato farms. So it looks like a basin because it's composed of, well, it has a surface a lot of glacial deposits, sands, and gravels. So it seems like there was a pre-existing topographic depression in that area, and the lake probably formed in one of those depressions.
Joe Richardson is asking what commercial mining is currently taking place today?
That's a good question. Let's see. There is mining of elastonite that is taking place in the eastern Adirondacks near Willsboro. There's also mining of elastonite over near Natural Bridge in Harrisville in the western Adirondacks. There is mining of marble in St. Lawrence County north of Gouverneur. It mostly goes for agricultural lime or decoration stone. It's a very pure white dolomitic marble. There is no mining of talc anymore. The zinc mines have shut down, although there is rumor that someone may buy them and reopen them. So, and there is still some garnet mining in North Creek at Ruby Ruby Mountain. Other than that, there is a graben filled with Ordovician limestone down in Wells, New York, which is mined for road metal. But other than that, it's mostly sand and gravel pits.
A question from John Newton. It says, can quartzites and other metamorphosed sedimentary rocks be dated to when they were sedimentary rocks, pre-metamorphosed?
It's kind of tough to do. However, you can constrain their age. You can constrain it using detrital zircons. There has been some work on the lutetium hafnium system. The lower marble up here in the Canton area and Gouverneur area has been dated by lutetium hafnium on apatite, and the age obtained was about 1275 million years. And they believe that age to be the time of the diagenetic growth of apatite in the carbonate rock itself. So it's a little more difficult to date than an igneous rock, but it can be done. Most frequently, people try to identify volcanic sequences in a sedimentary sequence and then use the volcanic rocks to date the sequence.
Another question, this one's coming from Nick Garson. It says, what are the greatest breakthroughs in our understanding of Adirondack geology in the past 5 years? And then on the flip side, what don't we know or can't know at the present time?
Well, that's a great question. And, you know, obviously I'm biased, but there's increasing recognition of fault zones, shear zones that have played an important role in the Adirondacks. And Graham Baird, who asked one of the earlier questions, is actually has worked on a shear zone up near Black Lake, which we now think is the margin of Laurentia during the time that the Adirondacks were forming. It seems to be a tectonic or terrain boundary. There's also another shear zone down in the southern Adirondacks, the Pacico shear zone, which seems to be a fundamental tectonic boundary. And so the dynamics, the kinematics and dynamics and the age of these shear zones are very important. But I guess if I had to pick one thing, we have come to realize that most of the structure, if not all the structure we see in the Adirondacks, predates what's known as the Ottoan origin. And the Ottoman origin, we used to think, was the primary deformational period in the Adirondacks history. It looks like it was more of a thermal event, and there's very little evidence that it resulted in any of the major structures that we see. So this dating of deformation and metamorphism seems to be one of the major breakthroughs. What don't we know? Well, there's a lot of things we don't know. One of the things that's constantly on my mind is whether or not the sedimentary rocks in the Adirondack lowlands right here on campus were deposited on a basement that we can find, or whether they have been thrusted off that basement. In essence, whether they are autochthonous or allochthonous. Allochthonous meaning that they were lifted off the basin and thrusted away from it. And so there's some speculation on what those basement rocks may be and where they might be, or whether or not they even exist.
Okay, it looks like we have a question from Karen Heath. We'll try to take that one live. Karen, did you want to go ahead and ask your question?
Is there a major difference between the northern Adirondacks and the southern Adirondacks geology?
Yes. If I had my own opportunity to subdivide things, I'd probably make 3 fundamental subdivisions, or maybe 4. Certainly the lowlands would be separate. They have a lot of different properties from the rest of the Adirondack highlands. The southern Adirondacks are also a bit different because they contain these 1.3 to 1.4 tonalitic arc rocks that seem to be lacking in most of the rest of the highlands. So we have at least 3 fundamental subdivisions that could be made, and there's probably more. Some people argue that the eastern Adirondacks is more like the lowlands than the highlands. Certainly the rocks are very similar. So yeah, it looks like there's some fundamental differences in age, and many of these are subdivided by major structures that indicate that they had a different origin prior to assembly.
Another question from Stephen Daniel is asking, why do we see lots of marble in parts of St. Lawrence County and not so much in the rest of the Adirondacks?
Yeah, that's also a great question. If you look at the New York State Geological map, you'll see in the Adirondack lowlands, which St. Lawrence County makes up a large portion of, a lot of blue, and those are the marble-related units. And then if you look down into the highlands, you see very little. But the same is also true for other metasedimentary lithologies, like politic gneisses and quartzites. They tend to be much more abundant in the lowlands and not so abundant in the highlands. And one of the reasons for that is the highlands is dominated by metamorphosed igneous rocks. The volume of igneous rocks in the highlands is just incredible. One estimate puts it at 60 to 65%. So we know the highlands has been heavily intruded, and the sedimentary rocks have been broken up and occur mostly as thin keels in between these large plutons. So it's in part probably a function of the depths that we're looking at. The lowlands were buried not quite as far deep in the earth as the highlands, and the highlands are much more heavily intruded, and as a consequence have less metasedimentary rock around the intrusion.
Okay, it looks like we have one more question right now from Dean Epler. It says, Jeff, if you had to guess how much of the crust was exposed in the Adirondack and the Grenville. And then he says, by the way, the Belchers have been a suspected impact structure for a long time, but they've never found shocked rock, planar structures, or any evidence of impact overprinting.
So there's part of the answer with the Belchers. How to guess how much crust was exposed in the Adirondacks and the Grenville? Oh, probably he means the depth. I don't have any a priori knowledge of that, but reading the literature, people have said that the Adirondacks was definitely one of these continental collision areas, like India in the Himalayas, where India is being snubbed under the southern margin of Asia. So the continental crust is double thick in there, maybe 70 kilometers thick. So people have argued that the Adirondacks are either the very base of the upper plate or the very top of the lower plate. Given the fact that we have a whole bunch of metasedimentary rocks, maybe the top of the lower plate is the best guess, 30 to 40 kilometers, maybe more. All right, this is one of my favorite cartoons provided to me by an alumni out in Idaho, and you can all read it, but the basic premise of this particular cartoon is that geology is just liquor and guessing. And while that's cute, not so much anymore. Part of modern geology is, we have an arsenal, an array of very sophisticated tools, and I've always thought of geology that we're probably the best borrower of any of these sciences, right? We have a geochemistry and geophysics and geomathematics and geobio, whatever, you can combine them all together. And one of the things that means is that the same tools that they use in physics and chemistry, we have adapted for use as geologists. And these are some pictures. Actually, the one on the left is in there reversed, right, at 1.5 tons. That's the shrimp facility up in Ottawa, Canada, that I've had a chance to use several times. And the shrimp is this enormous instrument that combines the properties of an electron microprobe, the small sample size, with a mass spectrometer. So it allows you to take radiometric minerals and focus in on discrete parts of an individual grain and analyze it. So you can analyze the core and the rim like I showed earlier. And it literally takes up a room about 30 feet long and maybe 20 feet wide. You actually sit in a room that's the machine's in a climate-controlled room. You're in the control booth behind glass. And the shot on the right just shows some of the complicated electronics that is required to run this machine. So liquor and guessing, not so much. That's for after the data is collected. One of the things that I really enjoy about my job is the ability to take students to analytical facilities, and it allows us to participate in geologic research that we probably couldn't do otherwise, because a small school cannot justify or afford some of this fancy equipment. And so this was back in 2013 down at the Arizona Lasercron Center. And it's a lab that's been set up at the University of Arizona exclusively for dating detrital zircons. In other words, zircons that have been separated out of sedimentary rocks. And the reason you would want to do this so where you can see the source where these rocks have been, the source material, the age of the source material. And so I've had the opportunity to go down there with several groups of students. We've also gone up to Carleton to use the samarium neodymium isotope lab, and UMass, and you name it, many, many places. Next one. And the two students that were with me, Ashley Durham and Peter Christofferson, graduated that year, and they went down and they helped me collect an awful lot of data. And there's an ablation pit, and that is the formed by a laser that's focused on a zircon crystal. The laser isn't powerful enough to ablate a pit that's anywhere between 10 and 30 microns across and about a micron deep. And so you can focus this laser on any part of a zircon as long as it's big enough, and you can blast away the material, and that material gets swept electrostatically into a mass spectrometer, and you can measure the uranium, thorium, and lead ratio. So those samples that those guys were working on, Ashley and Peter, were collected from several places in the stratigraphy of the Grenville rocks in the Adirondack lowlands. And I put those little gray zircon crystals to indicate. So we collected about several kilograms each of these samples from quartzite-bearing layers. They're from various positions in the stratigraphy, which consists of the lower marble, the Poplar Hill gneiss, and then the upper marble. And we use them to determine the age of the source region of that sediment. Now I want you to focus for a second, if you would, on the upper marble. You can see that it's been subdivided. And part of the reason so much is known about the upper marble, it's been subdivided into 16 units, is because that's where the famous Valmet zinc deposits are located. So there's actually 3 horizons in the upper marble that contain zinc, and that structure that contains them, it's called the Sylvia Lake Synform, has been penetrated by thousands of diamond drill core holes. So they drill down into the earth, they bring the core to the surface, the core is logged, and because of this level of detail, they've been able to subdivide that unit into 16 subunits. The other units, which don't have any economic interest in them, not that much is known about them, but the upper marble is very well characterized. So there's our samples. The first one there at the bottom is from quartzite layers, and the turbidites, remember the mustard-colored rocks that I showed you? We sampled the very thin quartz-rich layers. That's where that first sample came from. Then we sampled a quartzite-rich layer in the lower marble, and then we sampled another quartzite in drill core that was right at the boundary between the Poplar Hill Gneiss and the upper marble. So here's one of our sampling locations. This is from Richville, New York, right along Route 11. That's Roseanne Limbuso for scale, 1.676 meters. She is standing just below the unit that's outlined with the yellow dash. That's a quartzite unit, and that quartzite occurs in a 50-kilometer long belt of tourmaline-bearing gneisses. They're mostly arcosic in composition, quartz and feldspar, but some of them have as much as 50% tourmaline. That's another great unanswered question. Where did all that tourmaline come from? But we'll leave that one alone for a second, and we'll talk about what the results from the zircons we separated from that quartz-rich layer look like. So here's what the zircons look like. You can see that they're just over about 100 microns, which is fortunate because the beam size that we use to analyze them is about 30 microns. You can see that they're kind of rounded. Some of them have some hints of euhedral faces, but you can see the zoning. That's a backscatter SEM photograph. Shows difference in composition in the zircon material. Most of them are fairly well zoned. The metamorphic effects on them are very minimal. At best, a few micron thick metamorphic rims that give you those euhedral faces that would have been worn off if they were original. Next picture. This just blows it up a little bit. You can see the grain with the scale bar, 25 microns. You can see that it does have some metamorphic zircons, some very straight faces. But the interior of the crystal is very nice. Many of them show zoning, truncation of zoning, indicating that they rolled around and some of the crystal was busted. There's one down there that has a lot of inclusions. It looks like it has the measles. Next slide. So when we looked at these rocks, at the zircon populations, we got a scattering of ages that went from about 1.3 back to all the way to 3.2 billion years old. And that histogram shows us the number of analyses for a given age, broken up into about 25 million year brackets. And then the red is the cumulative histogram if you look at it statistically. And so the higher the peaks, the more of that particular age. So you can see that about 1.8 we have a maximum. There's also a big maximum of about 1.3. But we have scattered zircons of many, many ages all the way back to 3.2 billion years. So we can interpret this data. So that tan, gray, whatever that color is the age of the sources of the sediment that were eroded away to form this quartzite. And we have taken the youngest zircon to give us the maximum age of deposition. So that rock can really be no older than about 1250 million years. So that's a good approximation of the age of that quartzite when it was actually laid down. All the other zircons in it are older and come from the source terrain. So if you look at several of these samples together, very interesting picture emerges. The Pyrades quartzite, that mustard-colored rock with a big isoclinal fold, gave essentially a monomineralic population of zircons. They were something like 1290 plus or minus 7. We did 100 grains. got the same number each time. There's a few scattered ones, you know, 1 or 2 analyses that are a little bit older, but essentially dominated by a single population. If you move up in the stratigraphy, the lower marble, that's the one that I just showed you. And if you go all the way up to the top, to the boundary of the Poplar Hill gneiss and the upper marble, it has a picture very much like the lower marble, very wide source. I just want to point out the Poplar Hill gneiss. This was done by another technique by other workers, Human et al., and Bruce Selleck, Pat Bickford from Syracuse University were involved. And what they found in the Poplar Hill gneiss is that they mostly found metamorphic zircon. The Poplar Hill gneiss is the rock I showed you that was melted. So a lot of the zircon has rims of metamorphic zircon, and that's the big blue peak. And that gives you the approximate time of the melting of the rock. And then the little peak just to the right of it tells you the time of the source of the sediment. And it was very restricted, about 1.3 to 1.4, and no older Proterozoic or Archean zircons. So these samples, like the Pyrdes quartzite and the Poplar Hill gneiss, have very restricted sources, whereas the lower marble and the upper marble have very wide sources. So where do they come from? So here's a picture. If you strip away the rocks that cover the Canadian Shield as it extends down into America, we now know enough to draw these different age terrains. So you can see the green one, for instance, that's the Superior Wyoming craton, and the rocks there are older than 2.5 billion years old. And you can see the 1.8 to 1.7 area, known as the Yavapai province, and the 1.9 to 1.8 in brown, which is known as the Pinokian or Makovic province. So all these provinces have been described by others from work that they have done, and that red star shows us where our sampling location is in the Adirondacks. So there at the red star is where we actually sampled these samples, right here in the lowlands. Notice the cow and dolphin for scale. So all these ages are in billions of years. So one of the obvious things that we thought, since this area is on the margin of North America, that it probably should have a good percentage of zircons from the Superior province. Well, it turns out there are some, but some of the samples lack any. For instance, the Pyrdes sample and the Poplar Hill gneiss sample have no indication that there was transport from the Superior craton to the area of deposition. However, one of the interesting things we found is that some of the samples had very old zircons, and the closest place where you can find zircons that are older than 3.3 billion years are there at that black square known as the Winnipeg River terrain, and also the Minnesota River Valley. So the closest place that we could find zircons that old would have come all the way across the Great Lakes, which wouldn't have existed at that time, all the way to the Adirondacks. The biggest peaks in the upper marble and the lower marble were about 1.8, and those terrains are kind of in the center of the United States. Some of them are buried now, but certainly in the Great Lakes they're shown, and the 1.5 to 1.3 billion year old zircons have come from the granite rhyolite terrain, which is to the south and east. So it sure looks like there were massive river systems that were draining out of the interior of North America at that time, carrying zircons and quartz grains all the way, halfway across the continent, and depositing them at the edge of the continent, right where we sampled them. So to put this in some kind of analogy, down at the bottom you can see a cross-section of what it may have looked like as you went from the southern Adirondacks over to Ontario across the Grenville province. I have the southern Adirondacks shown as a separate entity. That's where the 1.3 to 1.4 billion year old arc rocks are located. I put a star where I think the rocks in the lowlands originated. It's called the Trans-Adirondack Basin. All the sedimentary rocks would have been deposited within that basin. The Frontenac terrain is a little older sliver of rock, similar to the southern Adirondacks and the Elsevier terrain. And then there was something called the metasedimentary belt, the central metasedimentary belt, where the rocks are very similar in terms of their sedimentology to those of the Adirondack Basin. So if you take this simple cross-section and you try and find a place on Earth where you have a similar tectonic situation, you can use Asia. And those red arrows kind of show you the different components. The first red arrow on the right shows you the subduction zone that exists off the coast of Japan. The arc itself is the Japanese arc. The Trans-Hudson Basin would be the Japan Sea or the Korean Sea, depending on whether you live on the east or the west. That little peninsula of Korea would be the Frontenac terrain, which actually the Korean peninsula has Precambrian rocks. And the central metasedimentary belt would be a failed rift, as shown there, in between Korea and China, and then the Asian mainland. So this is one possible analogy to what may have been going on in the Adirondacks. Now, remember that the Adirondacks have undergone continental collision, so all the components are crushed together. So this great width shown here between Japan and the continent of Asia has been telescoped down to a few hundred kilometers because of the deformation and the stacking of one terrain on another. So what's the take-home message? So our knowledge of the Adirondack region is expanding very rapidly as we have more and more tools in our arsenal to look at it. This new knowledge has driven new understanding of how the region formed and has evolved over time, and we can even look back to before the mountain building event by looking at these metasedimentary rocks. Much of this has been a consequence of the ability to date rocks using zircon and other minerals and date the events that they represent, because these zircons don't just date rocks, they date events. When were mountains formed? When were the rocks melted? When were plutons intruded? Even small undergraduate schools like our own can participate in this high-level research when we have access to large research institutions and the equipment that they have. And however, I just want to pet peeve, right, with many of us geologists, a lot of fancy black box equipment. I think I need a beer. Many fancy machines, but unless you understand the context of your samples, the field relationships, the data is often not interpreted correctly. So we'll take another break for questions.
We might have a few others out here. Okay, this one is from Graham Baird. It says, couldn't the source of the detrital zircons be from a continent to the east and not North America? I would expect to see 1.4 zircons if they were coming from the Yavapai, not pronouncing that correctly, territory.
Well, one of the reasons we don't believe the zircons are coming from the east is because there's every evidence that there was a fairly large body of water and that the rocks on the Adirondacks were deposited on the margin of Laurentia. However, if you step down to the Hudson Highlands, and I've done some detrital zircon work there, you actually see zircons coming off what we think was Amazonia. Some of the zircon dates match what was happening there. So we don't expect to see much coming from the south or the east. However, once the basin starts to collapse and the southern Adirondacks get closer and closer to the lowlands, that's when the Popple Hill was deposited, and we see lots of zircons between 1.3 and 1.4 billion years ago, and no zircons from the Canadian Shield, nothing from the Archean or early Paleoproterozoic.
This one's coming from Dwayne Epler. It says, in what environment do zircon crystals form in the first place, and what was going on in the source rock when they formed?
Well, most zircons form in igneous magmas, and in general felsic to intermediate. so they actually crystallize in a magma. And many of them form kind of early on because they have those very sharp euhedral faces, and as the magma composition changes, they become zoned in their trace elements. So most of them form in an igneous environment. However, you can also get zircon forming in metamorphic environments. It can form as separate discrete crystals or rims on pre-existing grains. I'm not aware of too many instances where they form in a sedimentary environment. In fact, I can't really recall any. So I don't think that that's a feasible way to form zircon, but certainly in higher grade metamorphic rocks and predominantly in igneous rocks.
Dean is also asking, where did the anorthosites come from?
Where did the anorthosites come from? Well, again, I have my own ideas on this, and one of my ideas is goes back a long time. It's been proposed by others, but apparently to get that volume of magma in the highlands, it requires something fundamental to happen in the mantle. You have to bring enough mantle material up closer to the surface so you get enough partial melting to make the gabbros that eventually fractionally crystallize to form the anorthosites. And one of the models that has been proposed by Jim McCollin and many others is that you had delamination. So following a collision event, you had a downgoing slab, subducted slab, break off. When that slab breaks off, it kind of creates room for the asthenosphere to rise up underneath the continent. And as it rises, it starts to melt by decompressional melting. So it usually, the thought is something catastrophic happening in the mantle, perhaps delamination and the rise of the mantle and massive amounts of melting. Those magmas rise up into the crust, and because they're hotter than the melting temperature of crustal rocks, they also start to melt, and you get this dichotomy of anorthosite gabbro and then more granitic lithologies.
John Chisholm is asking, have you read The Map That Changed the World by Simon Winchester about William Smith, the geologist? So could you comment on his contribution to the study of geology?
Oh my gosh, we were just talking about that this weekend. Yes, I have. I've actually seen an original copy of his map at a geological meeting in Buffalo. It was one heck of a piece of work. And, talk about someone who put in an enormous amount of time at personal sacrifice, financial and family life, to ride around in a carriage, in the early 18 teens in England and do this work. It was just phenomenal. And his map, there were so many interesting features. The fact that he shaded it towards the bottom, it was a darker color, and he used fossils to subdivide the units. So it was an amazing contribution. It's considered the first real geologic map. I mean, they find maps of quarry areas from the Egyptians and other cultures, but his was the first real understanding of how rocks are laid down and deposited.
Peterson has another question. Hypothetically, do zircons drift within rocks, or do they embed permanently? And then sort of as a follow-up, it says, since we know the time of Adirondack rock formation, can one estimate drift speed and estimate distance and therefore likely source of the 3 billion year zircon?
Okay. If they crystallize in a magma, they're usually entombed in rock. And the only way really to get them out is to physically and chemically break down the surrounding rock and liberate them. And if that's what you mean by drift, once they become liberated, depending on their size, they can be moved by a number of different agents of erosion and transport. If they're small enough, I suppose you could even transport them as silt-sized grains, by wind. Water certainly does it. Glacial ice can move them. And however, it would be a stretch, I think, to be able to calculate how fast they're moving. In fact, many of the zircons that wound up in those Adirondack rocks, or even in the Pakistan sandstone for that matter, may have gone through several cycles of erosion and retransportation and redeposition. So they may have been part of a sandstone that was intermediate in age between the source and the final resting place. so it's hard to calculate how fast they move.
So it looks like we have one final question here. It seems like an appropriate question to end on. Tyler Harris is asking if you have any new research projects coming up.
Yes, we were very, very fortunate. About a year ago, a man showed up outside my office, very modest, humble man, with a great knowledge of mineralogy. His name is George Robinson. He worked for years at the Canadian National Museum. He was the head curator, and then he went to the Seaman Museum up in northern Michigan. And George relocated to St. Lawrence County because it's such a fine place to study minerals. And he was wondering if there was any way that he could help out and collaborate with me. And it's just been a real pleasure to have him and his wife Susan here. And George has turned me on to some of the most fantastic mineral locations in St. Lawrence County. And the contribution that I'm trying to make is to actually date and understand these mineral localities. Many of these, like Powers Farm, have been known for 200 years. People have collected black tourmalines from Powers Farm and Pierpont for over 200 years. But very little information is known about the age or how it formed. So the contribution that I would like to make working with George and my students is actually understanding how these world-class mineral deposits formed and when. So now for a few practical applications of what we know about the Adirondack region. Over there on the left from that website, Andy Arthur, you can see the location of where hay and pasture and corn is grown in the northern New York region. On that is superimposed the Adirondack blue line. And you can see, aside for some areas around Lake Champlain, that there is virtually very little agriculture in the Adirondack region. And part of the reason for that is the poor soils and the rocky nature of the region. So the Adirondack Dome, the blue line, inadvertently or not, was drawn almost at the contact between the Paleozoic rocks and the Adirondack basement rocks, and it's just not a good place to farm. Along with that, everybody I'm sure is familiar with acid rain and acid precipitation. And yes, northeastern parts of the United States receive some of the highest acid deposition rates in the country. And the Adirondacks and parts of New England have long been known to be impacted by acid rain. We've made some major strides in reducing sulfur emissions, not so much nitrogen emissions because of all the vehicles on the road, but sulfur has been reduced. And it turns out, if you go back and look at the studies that were done 2 or 3 decades ago of acidification of the Adirondacks and go back and revisit the lakes, and I did this with one of my students, Michael Trumbauer. We picked about 40 lakes and went back and resampled them. You find out that some of the lakes have made some improvement. Some of the lakes have not changed, and other lakes have gotten worse. So it's really a wash whether much improvement is being made or not. And that, again, relates to the geology of the region. In the Adirondack lowlands, you can see that the acid neutralizing capacity of the rocks fall in category 4, which is very high, meaning the rocks in the lowlands around here can neutralize acid very well. The acid rain falls on the rocks, and the rocks can actually turn it into less acidity by reacting with the acid. And those green areas are areas that are underlain by marble. So someone asked a question about why is there so much marble in the lowlands. Well, not only is there a lot of marble, it helps us maintain lower pH conditions in the rivers. And I've actually done some studies with my students where we've looked at the rivers that start in the highlands and go into the lowlands. And the minute you cross over into a marble-bearing area, the pH will jump up dramatically as the rocks start to buffer the waters. You can see that there's some patches of marble over in the eastern Adirondacks and in the Newcomb area right beneath the Marcy Massif. So one of the reasons we're still battling with acidic precipitation is that vast areas in the western Adirondacks and the northern Adirondacks and the central Adirondacks have rocks that have little or no capacity to buffer acidity. So as long as there's going to be acidic precipitation, those lakes will not recover. So we think about climate change, and you can argue, what's driving it, but usually we're thinking in terms of temperature. But one of the things that I started thinking about was not so much temperature, but rainfall, and there have been some initial indications that most of the northeastern United States actually has experienced enhancement of rainfall. So I got a hold off the USGS site for my hydrology class a bunch of data sets for different rivers draining the Adirondack Dome, and we looked back as much as about 104 years. And what we found over the record-keeping period, on the average for those rivers that are listed there, that there is now 19% more water flowing through the rivers than there was 100 years ago. And you can see that trend. There are various cycles, but you can see the upward trend in the dashed line. And that particular one that's shown is for the Racket River. So it looks fairly certain that the Adirondack region over the last 100 years has been getting wetter and wetter. Landslides. I think it looks like we're running out of time, so if you would go on, I'll just get to the end of this. Keep going, keep going. I just want to show them one more. Here we go. Okay, ore minerals. Let me just take a couple minutes here. The Adirondacks is a treasure trove of very interesting ores. One of them is the titanium deposits down at Tahalis. That's the old smelter. Right here in our backyard near Governor, we have the sphalerite or zinc deposits. There's massive garnet deposits near North Creek. And locally in St. Lawrence County, we have some world-class mineral deposits. And that's Mike Walters. He's a local collector from Parishville, New York. Brings his students every year. He's a high school teacher. Brings his geology honors class to the geology department every January. And there is a picture of the beautiful black tourmalines from Powers Farm. Next slide. So last March, we went down to Arizona again, one more, with Thomas Lockwood there in the background and Hillary Hagen-Peter in the foreground. And we took zircons from some of the mineral deposits, and I wanted to show you some of the newest results, and this is from Powers Farm. On your right is a cathode luminescence SEM photo of a highly zoned zircon with beautiful euhedral shapes. That is from Powers Farm. I took it from a rock composed of tourmaline, quartz, and calcite. Surprisingly, it contains zircons. And the age that we obtained was 1158 plus or minus 3 million years. Very well constrained age. So we now can say without any measure of doubt that that is an igneous intrusion. It's a dike. Those tourmaline hosted veins are all dikes, and that they were intruded during the end of the Shawinigan orogeny at about 1158. So the take-home message for the whole talk: it's a lot of fun to get paid to look at rocks. And there's your bouncing zircon. Keep going. And just one other thing, I'd just like to acknowledge a bunch of people and thank them. I was a student here. I was highly influenced by my professors, including Drs. Elverty, Jacoby, Shar Mertens at UVM, and Bill Romey. I also had the initial opportunity to start working on the Adirondacks through Ingvar Isaacson and Phil Whitney of the New York State Museum, Jim McClellan of Colgate, and the funding. And this is a very important part of this. I would not have been able to do a lot of this work if it wasn't for our alumni contributors. They contribute to the James S. Street Fund, which is set up for student research. It allows me to take students with me to Arizona to do this work. So thanks to you all, thanks to the students, and thanks to my many collaborators over the years. Thank you for your attention.
Great. Thanks so much, Jeff, for leading tonight's lecture, and thanks to all of our participants for your great questions. When the webinar concludes, you'll get a brief link to a survey. I hope you just take a moment to answer the 3 or 4 questions that are there, and your feedback will certainly help to shape future lectures. So thanks to all of you, and have a great night.
Thank you.